everyone, today I'm going to be talking about Newton's second law as it applies to constant velocity motion. For this experiment, I observed and recorded a lacrosse ball rolling across a level surface at approximately constant velocity. I then imported this video into the program Tracker for analysis. Next, I determined the frame of reference for the video using the diameter of the lacrosse ball in meters. I then set up the coordinate system with the positive y being in this upward direction, negative y being in the downward direction, positive x being in the right direction, and negative x being in the left direction. The ball then continued to go across in the positive x direction. As you can see, the axis is centered at the center of the ball at t equals 0. The coordinate system, as you can see, is tilted slightly upward. This was necessary because if I had not done this, the ball not only would have a velocity in the x direction, but y as well, due to the angle of this video, which is not the case in the constant motion of an object on a flat surface. Also, I could have chosen another orientation of this coordinate system, but this would have then also changed the vectors for velocity. I felt that it was best to have the ball moving in the positive x direction to best show its motion. Even though I did my best to orient the axis so that the ball would travel in a straight line along the positive x direction, there is still some magnitude in the y vector. However, since this is constant velocity motion in one direction, the y and z values are not important. First, I input the known value of the ball's mass. Then I inserted the initial position from Tracker and the ball's initial velocity, which was calculated from the first two data points in Tracker. There is a y value, as you can see here, simply because of the angle of the recording and the human error of my close but not exact plotting. In the physical world, this would not be the case. I then use this info to predict the ball's future motion in the loop while the time t is less than 1.267, the ending time of the video segment. Both the new velocity and new position of the ball were found by manipulating Newton's second law. It is important to note that this model assumes constant velocity, so the net force acting on the ball is equal to 0, as is seen in the code. We do not know which forces, in which direction or magnitude, or even how many are acting on this object, but this is not important, as long as they add up to 0, giving us constant velocity. The model data was then exported and combined with the experimental data for comparison. As you can see, the model data forms this orange straight line, and the experimental data forms these series of points. The two position versus time graphs are similar just in the beginning, as you can see here. But then it appears that the ball had continued to accelerate, traveling at a velocity slightly faster than that of the constant velocity of the model. When creating the model, I assumed 0 net force, meaning that the ball traveled with constant velocity. However, this probably was not the case during the experiment. There were forces acting on the object such as friction and air resistance. Also, though I tried to select a part of the video in which the ball appeared to be moving at constant velocity, I am only human, so it is likely that the ball could have still been accelerating at this point, which would account for the difference in the velocities between the model and the experiment. The ball also did not travel in a straight line as best I tried. It spun slightly and moved toward the back of the table. In addition, the plots I pointed in Tracker could have not been exact, which would have caused further discrepancies between the model and the experimental data. Thank you for watching my video.